Hello everyone and welcome to the MIDAS webinar on Global Analysis to the Detailed FEA Analysis using MIDAS Civil NX and MIDAS FEA NX softwares. My name is Pratap Zado and I'm working as Technical Support Engineer with over 8 years of experience at MIDAS, working across the bridges as well as building sector. This webinar demonstrates how to effectively generate a global to the local model using the synergy of MIDAS Civil NX and MIDAS FEA NX integrations. The session covers a short overview of the capabilities of MIDAS Civil NX and MIDAS FEA NX. In the following, the global modeling, analysis of the prestressed girder using the MIDAS FEA NX will be discussed and demonstrated. Now let us discuss about the contents for this webinar. First, we will discuss about the MIDAS FEA NX software, following the major capabilities of the software, different analysis options, as well as the features which are required for detailed analysis such as nonlinear buckling analysis, and so on. Then we will move for the MIDAS Civil NX to MIDAS FEA NX integration. I will also give a short demonstration for the analysis of one of the bridge girder with external prestressing, where how the MIDAS Civil NX model can be integrated with the MIDAS FEA NX. And finally, we will end up with the summary and Q&A. So about MIDAS FEA NX, MIDAS FEA NX is a linear and nonlinear detail analysis program. It can be expressed in a major four ways. First is the engineering exclusive. MIDAS FEA NX is a specialized civil engineering finite element software. It provides a user-friendly modeling environment and database for the detailed analysis. Second is diverse program integration. So it connects not only among the MIDAS software in MIDAS collection, but also with the various 3D CAD file formats. Third is excellent mesh generation. When creating a mesh for a geometric shapes, various techniques and hybrids can be employed to generate exceptional quality finite element models. For analyzed advanced analysis, MIDAS FENX offers a diverse simulation environment employing high performance solvers and parallel computing techniques for swift analysis. Let us know the major capabilities of the software. So it is a accurate and reliable diverse finite element analysis software. It also supports a wide range of specialized analysis including nonlinear analysis using innovative modeling techniques and practical analysis functions to be applied effectively in real-world scenarios. It also includes the various analysis capabilities such as linear analysis, construction stage analysis, modal analysis, buckling analysis. We can also add the reinforcement for the checking the stiffness of the reinforcement for the account of stresses and the forces. Nonlinear analysis, which consists of for both steel as well as for concrete. Heat of hydration analysis, dynamic analysis, and fatigue analysis. So these are the various applications where the MIDAS FENX will be a will supports for the range of specialized analysis. So here we will discuss about the integration between MIDAS Civil NX to the MIDAS FENX program. So we are talking here about the global to localized model approach for more detailed analysis of any bridge or structure component using this MIDAS FENX software. So as we already discussed it's a support a range of specialized analysis. Now we will first start with the global structural analysis using MIDAS Civil NX software. Okay. So it can be for the grillage or for the simple line modeling. Then we will carry out all the loadings and the different analysis, and we'll just check for the global analysis effect. Then we'll transfer the model from the MIDAS Civil NX to the MIDAS FE NX. We'll update the geometry in the FE NX for more refined and detailed analysis by customizing the boundary condition, applying certain load over the maybe a solid model, and we'll add certain non-linear as well as the dynamic analysis. Then we'll perform this analysis and we'll check some results in terms of stresses as well as for the forces. Then we'll validate these particular results either with the experimental result or with the theoretical results. During the demonstration, we will discuss about how to model a particular tendons with a deviator blocks, how to apply the prestressing force, how to consider the connectivity between the newly added members with the geometry imported from MIDAS Civil NX software, application of the prestressed. Along with that, we can also simulate the construction stage analysis, addition of the reinforcements, and whether the structure need to be analyzed with nonlinear or without nonlinear parameters. So in this demo, we will discuss about the four things. First, to import the geometry of the beam element and the tendon profiles from MIDAS Civil NX to the FE NX, how the model can be considered for the external tendons in a beam with the additional modeling of the deviator blocks, how to define the prestressed loads in the FE NX software, and then we'll check for some specific results that can be extracted for our project purpose. Okay. First, let me explain about the MIDAS Civil NX model, which is prepared for a prestressed eye girder with the external tendon. So first, I just open the works tree with the defined inputs. Here we have prepared this particular beam with the line element that is showing here. We haven't created any further division, just have put only the three beams with the four nodes. For the material properties, we have considered the Eurocode and the Y1816S7 15.2 mm property for the tendon and C4050 grade concrete for the concrete area. Section wise, we have used the built-in cross section for the PSC girder. It is without the slab, of course. So just we have considered a typical cross section, and these are the details for that one. In the tendon property, if you see, so we have considered here the external type of prestressing, which requires only the data like how many number of like what is the tendon total tendon area, relaxation coefficient, ultimate strength and yield strength, and the anchorage slip. For the tendon profile, we just used a simple profile. Okay, so here we have assigned this for this particular selected elements, and then these are the coordinates which are specified into the model. So there are two tendons which are assigned here, which we can see here. Now we will discuss about how to export the MIDAS Civil NX model for integrating with the MIDAS FE NX. So we'll go to the file, export, and here frame section for solid. So there are two ways to export this particular model. One is you can export as a MCT so that it will You can export this file as a MCS file. Okay, so that will be saved here. And second is the MCT. So MCS and MCT, these are the two extension which can be generated for FEA NX. We are creating for all the members and the tenant profiles as well. So just click on OK, and this will be saved in a MCS file format. So I'm just giving the name MIDAS Civil NX model, let's say 1, and then click on save. So this generate the MCS file. It's similar to the MCT. So these are the element groups, the lines, the sections, and for the tendons, so we'll have the tendon data as well. Okay. Now, so we'll now go to the FEA NX software. So just go to the file and new project. Before we proceed for the actual demonstration, let me just quickly give the overview of the software. So just I will change the units to Newton mm and click on OK. Here the interface quite similar to the MIDAS Civil NX except the functionality. So we have the file menu, main ribbon menu, there are model menu, okay, which has 3 tabs under that, just like a tree menu in the MIDAS Civil NX. And then we have the model window, followed with the message window, which can show any error or warning during the analysis, and the shortcut toolbars that can be controlled based on our utility. So now if we go to the file, and then I'll first save this particular model file, giving the name as MIDAS FEA NX model 1. We'll go to the frame to solid, and here we'll select the MCS file which we have generated. We'll give the name here as girder and then click on OK. So this will import the geometry for the eye girder, along with that the tendon profiles as well. Now we need to create the deviator blocks, as it is a external prestressing. So we need to create the deviator blocks separately outside the eye girder. For modeling that one, we will have this particular function called geometry. We'll go to the box option, and here we'll specify the coordinate to be required at generating the deviator block. So just I will specify the coordinate, let's say 0, 150, minus 1450, and here it will be 300 by 300 by 300. That is actually the cross section of this particular deviator blocks. We'll give the geometry set as deviator block and then click on OK. So one deviator block has been generated here. We can go to the geometry and you can just turn off the girder so that we can able to see this particular deviator block here. Okay. I will again turn on the girder here. We will copy this particular deviator block, okay, at a certain distances. So I will select this particular deviator block, or you can just double click there and use the translate command. So already one target section has been selected, and select the direction. I need to copy this. So in the FEA NX, this is the x-axis, y-axis, and the vertical is z. I need to copy this deviator block from left to the right. So I will select the direction. Okay, direction is selected. Select the copy and then specify the distance as minus 600. We are going in the negative y-axis. Click, and it's the same geometry set as deviator block. Click on apply. So the deviator block get copied from here. Again, select both the deviator blocks. So select the target, select it. Two deviator blocks will be selected. Select the direction now as X. Okay, we are going to copy now along the X direction. Specify the distance. In copy, it is 9850, and then click on apply. So the two deviator blocks has been copied. Again, I'm selecting specifying the distance. So it's a relative the distance, sorry, it's absolute distance now. So we are specifying again the distance is 19850. click on apply, and one more at the end location, which is 30,000 minus that 300, so it will be 29700. Okay, and then click on OK. So this way we have created total 8 deviator blocks. If we go to the front view here, so these deviator blocks are all at the soffit level, at the mid level, but there is a cable location here, right? So these two deviator blocks are correct. Now I will go to the again the translate command, and here I will select the objects. So this deviator blocks and this deviator blocks, total 4 deviator blocks, 2 on either side of this eye girder. Select the move, select the direction as Z, and then specify the distance to 900 in the upward direction. So it's again in the same geometry set. Click on OK. Now, as these deviator blocks are separately created, so we cannot sure about the connectivity. So that's why we will go to the auto connect feature and then select the whole geometry and click on OK. So this way it will connect all the geometry with each other. Now we need to specify the material properties. So I will go to the mesh and material properties. Here I am defining the two material, one is for concrete and second is for the tendon. So we'll go to the create and then isotropic material, that is for the concrete. So I'll give the name as concrete. Elastic property, we will go with the database or a user defined material. So we'll go to the DB, select the concrete, select here the Euro code, and then select the C4050 grade. Click on OK and then apply. Then I'm defining the tendon material, where we'll go to the DB and then we'll select here steel EN05PS and Y1860S7 15.2 mm. Click on OK, OK, and close. Now we need to define the properties. So first we define the material. Now we are defining the property. So three property we will define here. We'll go to the property, create. First is for the 1D, that is for the tendon. So we'll use the truss type of element for creating this external tendon. From material wise, we'll select here the tendon material. The area will be 2660, that is 19T15 standard material area, and then 1 mm raised to 4 and 1 mm as a torsional constant and torsional stress coefficient. If you want to define this manually, you can go with the option section, and here I can select the, let's say, the solid round shape with the actual diameter. Okay, so this is how we can define this property. So one is for external tendon, click on apply, and then we are defining okay, sorry, we'll cancel this, and then we will go with the 3D option because it's a 3D material for the concrete. We'll give the name as concrete and the concrete material from the list. Click on OK. Also, for considering the connection between these deviator blocks, okay, and where this particular tendon which we have prepared that need to be actually connected with the solid element, so we will define the rigid link as well. So for modeling this particular rigid link, we will go with the other property. In this other property, I will select the rigid link and then I will just give the name here rigid link and turn on the rigid body option. Click on OK. In case if you want to consider the time dependent material properties, so you can go to the again the 3D, sorry, we can go with the 1D, go to the I think it is in material, sorry. We'll go to the material, isotropic, select here the time dependent, and then you can go with the age dependent. In that we can go with the implicit, and for the creep shrinkage, same like a MIDAS civil NX, we have the European code where we can specify the loading, and then we can generate the step for that particular specific material properties, which we have defined already, the grade and other stuff. Similarly, for the elastic modulus as well, we can again specify this remaining property, and then you can, let's say, select the European code, and it will generate the variation of uh, modulus of elasticity with the time. Okay, close. So when we use to create the construction stage analysis, for that we need to define this time dependent material properties. Next will be, we will be creating the mesh. Okay, so this geometry is acting like a single member, right? So now we will go to the mesh option, and there are two options depending upon the type of property. So we have, first we have the 3D, that is for the solid. So in the 3D, we'll select the object, and then we'll specify here the mesh size. There is a two type of meshing. So we'll select here the hybrid mesher, select the concrete material, and then click on OK. So this generate the meshing for this selected elements. It also generate the meshing for the deviator blocks as well. Now we will go to the 1D mesh, because for the tendon which is already prepared by the truss element, that need to be also meshed. So here for the 1D, we'll select the division as 1, select the geometry, okay, where it will only select the tendons. Okay, we already divided that into the 3 part on either side, so total 6 objects. Select the external tendon, automesh 1D, and then click on OK. So this way the mesh has also been generated. Next will be the application of the boundary condition. We'll go to the front view, we'll go to the static analysis and constraint. We will consider the simply supported condition here. So we'll give the name as constraint 1, boundary set 1, click on pinned, and then select here the nodes which are considered for the application of the this pinned condition. Click on apply. Similarly, we'll go to the advanced, because just a roller support will not be sufficient as it is a 3D structure. So we'll select the 4 nodes at the soffit level on the other side, and then we will specify. So from the advanced option, I can turn on and turn off depending upon the requirement. So this will be also in the boundary set 1, constraint 2, and then click on OK. We need to apply here the load. So we'll apply the two types of loading. We'll go to the static analysis and self weight. I'll give the name here. Let's say the self weight load set is the default self weight, and the factor will be -1. We'll click on OK. Similarly, we will go to the prestress load, select the object for which the prestress need to be applied. Load case name is prestress 1, and here we can create another, that is a default, let's say prestress. We'll give the force in Newton. So let's consider 75% of UTS, 3500 000, that is almost 3500 kilonewton of force for this particular 1D element modeled as a truss or embedded truss element. Click on OK. Now we need to consider the rigid link which will connect between the deviator blocks. So here we will, from the mesh, we will remove this particular automesh 3D, and we'll just activate only the deviator blocks. So even this 3D also we can turn it off, so that it will be easy for the application of this particular rigid link. I'll zoom this, and then by control and the scroll button, I'll zoom this to the divider blocks. We'll select here the element, that the selection filter, and then select these two elements under the divider blocks. Right click and click on the hide. Now we will go to the, so here we are actually modeling the rigid link. So for that, we'll again go to the mesh option, create, and under the other option, we'll select the rigid link. Okay, just we'll save the file. Now under this rigid link, I will select the node, okay, the central node, and that is the master, and the slave nodes on the other side. So this will be added under the property rigid link, and the mesh set as rigid link. Click on apply. Again repeat the same procedure for the remaining location, master and slave nodes. Apply. We can select all the uh, elements together, otherwise you can just go with one by one. Hide. So we just hide it together. Okay. Yeah. So here we are assigning the rigid link now. So for assigning the rigid link, we'll go to the again create, other, and here the rigid link. So just select the master node and the slave node on other side. Apply. Master node, slave node other side. Apply. Master node, slave node on other side. Apply. Master node, slave node on other side. Apply. Master node and then slave node on other side. So I hope the procedure has been clear. Okay. So once it's completed, now you can activate all the mesh sets and then you can click on the ISO view. Next one will be performing the analysis. So let me go to the analysis menu, general. Here we can create the multiple cases. So for example, let's say you can create the n number of cases. So this is the linear analysis, okay, where I will select the linear analysis, and then there are the multiple load case. So you can assign all the mesh set, assign all the boundary condition, just drag and drop, and the static loads. If you want to control over the analysis control, you can select the data here, and in the output, which results you want, you can select that one. So just click on OK and then perform the analysis. Here you will ask, so it is basically the selective analysis feature which is already there from the past. We can select which type of analysis or the load case we wanted to perform. So we'll click on OK. The analysis has been completed. We'll go to the results. In the linear elastic, it will show the results in a case wise. So if you want to see the deformations, so this is the deformation of the structure. Now in the analysis case, okay, in the analysis case, If you want to solve each load case separately, you can turn it on, click on OK, and then perform the analysis again. So this way it will show the results separately, otherwise it will combine all the results together and it will give all the results. So now if we go to the results, so it will show the results separately for pre-stress and separately for self-weight. There is option where we can give the load combination as well. So just I will go to the results now, and here we'll see the results separately. So for the pre-stress loading, we'll go to the displacement and the deformation here. So as you can see in the front view, this is giving me the deformation of the structure in millimeter, that is 18.54 mm. There is an option, so say special options like a props, where we can just click anywhere to see how much deformation is taken place. Okay. Then separate options like suppose if I want to go for the grid forces, that is a applied force. Sorry, this is for actually the beam element, of course. So it won't be actually available. The reactions at the location where the support has been used. Then the forces in the truss type of element, how much the forces has been occurred. We can go to the ISO view here and we'll see this deformation forces here. So the truss type of element has been used. So for that we can see here, and the stresses into the member. So this also can be seen here. So what are the stresses here? Similarly, if you go to the self weight, so for the self weight, we can see the deformation of the structure, the grid forces. Then we have the reactions at the support location. So whether you want particularly the vertical reactions alone, they can select that. Then the other components based on the type of element we have used. So these are the stresses. Okay. So this is how the various results can be checked using this particular finite element modeling in the MIDAS FEA NX software. Just for the more detailed information, I just unlock the model. Now there are additional features as we have not discussed, but I just wanted to introduce it. So same like how we model this particular tendons, we can go to the again the mesh property, let's say the isotropic, and here how we define the material property for the we can say for the tendon. Same like that we can define the reinforcement as well. So that is also available in the database. And plus if we go to the property where for the 1D we will use the embedded truss option for creating the tendon reinforcement, where we can simply specify the area, or if you want to go for defining the diameter, that can be also possible here. To model it, we can go to the geometry and then simply we'll create the lines, okay, from a particular point where we wanted to generate the tendon reinforcement, and then use the translate command for assigning this particular reinforcement. After assigning this particular reinforcement and all, make sure that we are auto connecting this particular tendon reinforcements. Then there is also option for specifying the other loads. For example, if I go to the front view and if I wanted to apply certain force, let's say as a pressure, so then uh, we can use a particular command. Sorry, this is for the point loads. If we apply the pressure, so just I will select the top portion of this particular top flange of the structure. So let's say for the 3D face, top portion here, and then we can just create a load case, pressure case, specify certain intensity, and then apply that particular pressure here. Further loads such as temperature gradient, nodal temperature, so and many more that can be possible here. This is for creating the load combination. For example, if I create, let's say, the load combination 1, so this will give the list of the loads which we have created here. Suppose I will select the sulfate with factor 1.35, another with the factor, let's say 1, the next factor with the pressure with the factor 1.35. Likewise, and we can create this load combinations as well. When we go to the analysis, we can create the n number of cases. Let's say linear static 2, okay, in which I wanted to run only for the combination. So this also can be possible. When we perform the analysis, now it will ask whether to run for both or for only one of them. So we can run the analysis in this way. Once the analysis is completed, we'll go to the results, and here in the linear static 2, for the combined uh, cases, we will get this particular structural behavior like deformation or even the stresses, solid stresses that can be checked here. So this is how the different analysis options can be used using the MIDAS FEA NX. So thank you for attending today's webinar, and I hope this session will be helpful in your upcoming design works. So for any more details, kindly contact Manoj Khetarpal. So the details for communication has been provided here. So thank you once again and have a nice day.